In the early days of November 2025, a celestial event defied the sun's predictable influence. Emerging from intense solar radiation was an entity known as 3IATLAS. It appeared utterly still, remarkably compact, and defiantly unusual. While astronomical instruments anticipated a spectacle of solar chaos, they encountered an unnerving calm. There was no discernible tail, no hazy coma, and no visible dust. This object seemingly traversed the sun's turbulent storms without the slightest perturbation. Both the Naves Observatory and the Virtual Telescope project corroborated the profound concerns of scientists. A comet that disdained the established astronomical norms. Concurrently, at the Jet Propulsion Laboratory, analysts observed perplexing data. Subtle light fluctuations indicated movement devoid of any propulsive force, as though an invisible agent were guiding its course. What began as a straightforward comet designation rapidly transformed into a profound enigma, challenging the very fabric of physical laws. Was this phenomenon natural or engineered? Experts like Stephen Burns now contend it's not a comet at all, but rather an ancient artifact, dense and metallic, its origins lost to time, perhaps crafted, perhaps abandoned. Stay with me until the conclusion. If this hypothesis holds true, the fundamental question shifts from the identity of 3IATLAS to the identity of its creator. If this unfolding mystery captivates you as much as it has me, please express your engagement by liking this content and subscribing so you remain informed of every update as this unfolding narrative progresses in real time. Part 1 delves into the headline-making event. Envision this scenario. Early November of 2025. Astronomers worldwide are poised, their sophisticated instruments trained on a visitor from beyond our solar system. This celestial body, designated 3IATLAS, has just completed its closest approach to the sun. 1 week has passed since it reached perihelion, the pivotal juncture where the sun's intense heat should have transformed an icy comet into a dazzling exhibition of gas and dust. The Naves Observatory in Spain captures an image. The Virtual Telescope project in Italy performs a similar action. Scientists eagerly review their findings, and what they observe renders them speechless. The image depicts a sharp point-like light reminiscent of a star. There is no diffuse halo, no trailing tail extending away from the sun, and no luminous aura of sublimating ice. It is simply a single point against the vast darkness, as if an artist had placed a solitary pixel on the cosmic canvas. This outcome was entirely unanticipated. It is crucial to comprehend what the expected behavior was. This object achieved its closest point to the sun, perihelion, on October 29, 2025, at a distance of approximately 1.38 astronomical units from our star. This position is roughly 130 million miles situated between the orbits of Earth and Mars. For perspective, this proximity is sufficient for any typical comet laden with frozen volatile substances such as water ice, carbon dioxide ice, ammonia, and methane to experience significant heating. The sun's radiation would vaporize these ices, releasing streams of gas that carry dust particles along. We should be observing a coma, that nebulous cloud of gas and debris surrounding a comet's core. We should also be witnessing a tail, potentially extending for millions of miles, propelled away from the sun by solar winds and radiation pressure. This is fundamental cometary behavior. It is what comets do. 3IATLAS, however, appears to be unaware of these established principles. The timing of these observations further exacerbates the perplexity. Between October 29th and November 5th, the period during which these images were captured, the sun was far from quiescent. Recent solar disturbances had been bombarding the inner solar system with charged particles and intense radiation. Under such conditions, one would expect enhanced outgassing, leading to even more pronounced activity than usual. Solar storms are capable of stripping material from cometary surfaces, ionizing dust particles, and generally creating a dramatic display. Yet 3IATLAS persists in its star-like appearance, refusing to conform. This brings us to the central question, the mystery that will occupy us for the subsequent hours of investigation. Why the absence of outgassing? Why no classic tail or dusty coma? When all our physical models predict their presence, allow me to illustrate the standard model's prediction. A comet rich in volatile substances approaches the sun, solar heating intensifies. Ice begins to sublimate, a process where solid matter transitions directly into a gaseous state without an intermediate liquid phase. This sublimation generates pressure beneath the surface. Eventually, jets of gas erupt, expelling dust particles. The gas forms the coma, glowing as it absorbs and re-emits sunlight. The dust creates one tail, pushed by the sun's radiation pressure. Ionized gas forms a second tail, swept back by the solar wind. Both tails generally point away from the sun, producing the iconic cometary visage that humanity has documented for millennia. This is the established protocol. This is how it functions. 3IATLAS seemingly operates under a different set of rules, or perhaps no rules at all. This is not merely a peculiar comet exhibiting slightly unusual behavior. The discrepancy runs far deeper. We are potentially observing an object that challenges our fundamental classifications. Is it an icy comet, a metal-rich asteroid, or something entirely distinct? Something that defies easy categorization within the frameworks we have developed for understanding small celestial bodies. The implications of this single anomaly radiate outward like fissures spreading through ice. This investigation will unfold in 3 distinct parts. In the first part, we will establish the context, detailing the orbital mechanics, photometric data, observational chronology, and the core paradox that fuels this enigma. We will encounter the diverse perspectives within the scientific community, from those who maintain it is simply an atypical comet to those who propose far more extraordinary explanations. In the second part, we will delve into the anomalies and overlooked aspects, cataloging every peculiar characteristic of this object and exploring the potential meanings of each oddity. We will examine models of its composition, mechanisms of acceleration, and the perplexing issue of its motion, which suggests venting of material when no such venting is visually apparent. In the third part, we will broaden our perspective to connect this mystery with wider trends in scientific discovery, space exploration, and artificial intelligence. This is because 3IATLAS does not exist in isolation. It is part of a larger narrative concerning the unexpected discoveries we're making across multiple scientific frontiers. As we proceed, please bear the following in mind. This presentation will guide you through evidence, anomalies, speculation, and interpretation. Some of what we discuss is firmly established observational fact, while other parts are educated conjecture. I will clearly delineate between the two. By the end, you will be contemplating a question you likely never anticipated seriously considering. Is this a comet or something far more extraordinary, something originating from another star system that behaves unlike anything in our cosmic vicinity, something that might necessitate a complete re-evaluation of our understanding of interstellar visitors? And for those with a particularly imaginative outlook, something that may not be entirely natural. Therefore, please stay engaged, as what we are about to explore resides precisely at the intersection of the known and the unknown, between the explainable and the profoundly mysterious. And it is at this very boundary that the most intriguing questions emerge. Part 2 presents the latest orbital and photometric updates. Let us first establish a factual basis with concrete figures, as the trajectory of 3IATLAS conveys its own story even before we address the anomalies. This object is traversing our solar system on what astronomers term a hyperbolic orbit. While this designation sounds exotic, it simply signifies that this visitor is not gravitationally tethered to our sun. Unlike the comets and asteroids that originated within our solar system and follow perpetual elliptical paths, 3IATLAS originated elsewhere and is now returning to the void of interstellar space. It is a cosmic traveler that, by chance, passed through our region. The Jet Propulsion Laboratory and the Minor Planet Center have been meticulously tracking this object since its discovery, refining their calculations with each new observation. Its inbound velocity, relative to the sun's frame of reference, was approximately 33 kilometers per second. This equates to roughly 74,000 miles per hour, a speed that eclipses anything humanity has ever engineered. On October 29, 2025, it reached perihelion at a distance of approximately 1.38 astronomical units from the Sun. Subsequently, it commenced its outward trajectory, gradually increasing its speed as it ascends back into the Sun's gravitational influence, heading toward interstellar space. However, velocity and trajectory are not the sole parameters that astronomers have been measuring. Photometric observations, which involve measuring brightness and color, have revealed intriguing patterns. Since early October, observers have noted that 3IATLAS has been intensifying in brightness within the green wavelength band by a factor of approximately 5. This is not a subtle shift. It represents a dramatic surge in luminosity at specific wavelengths, suggesting that either the object's surface or its surrounding material is reacting to solar heating. Green emissions from comets typically indicate the presence of diatomic carbon molecules, C2, which emit green light when energized by sunlight. Consequently, this increase in brightness initially appeared to be a promising indicator of cometary activity. Except, as we've already established, there is no visible tail or substantial coma accompanying this enhanced luminosity. The photometric signature contradicts the visual appearance. Now let us address non-gravitational acceleration, as this is where the situation becomes genuinely perplexing. When astronomers plot an object's position over time, they can predict its trajectory based solely on gravitational forces exerted by the Sun, planets, and other massive celestial bodies. However, occasionally an object deviates from its predicted path, accelerating or decelerating in ways that gravity alone cannot account for. For typical comets, this non-gravitational acceleration arises from the reactive force of outgassing jets. Gas escaping from the sun-facing side of the nucleus propels the comet much like a minuscule, inefficient rocket engine. This effect is well understood and regularly quantified. 3IATLAS exhibits clear non-gravitational acceleration. The radial component, indicating acceleration directly towards or away from the Sun, measures approximately 1.1 times 10 to the power of -6 astronomical units per day squared. The transverse component, acceleration perpendicular to the line connecting the Sun and the object, measures about 3.7 times 10 to the power of -7 astronomical units per day squared. These are modest forces, but they are demonstrably real and measurable. Herein lies the illuminating and equally troubling mathematical aspect. If we assume typical cometary outgassing with gas ejected at approximately 300 meters per second, we can calculate the mass that must be expelled from the object to produce the observed acceleration. This calculation is contingent upon the object's mass, which we can estimate from its brightness and assumed composition. When these figures are analyzed, a startling outcome emerges. To generate this acceleration through conventional gas ejection, 3IATLAS would need to lose approximately 13% of its total mass during the observation period in question. 13%, consider this for a moment. Over 1/8 of the entire object would need to be expelled as gas and entrained dust. This is not a minor outburst. It is not gentle sublimation. It represents a colossal and sustained eruption of material that should be unequivocally detectable by any telescope trained upon it. It would be impossible to conceal such a significant loss of mass. The dust and gas would form an immense envelope around the nucleus, scattering and reflecting sunlight over a volume spanning millions of miles. We should be observing it blazing like a beacon in our images. We do not. This is the paradox in its starkest mathematical form. The observed motion implies substantial outgassing, while the images indicate virtually no outgassing. Under conventional cometary physics, both cannot be true. The observational timeline introduces another layer to this enigma. 3IATLAS was discovered on July 1, 2025 by the Atlas Survey, the asteroid terrestrial 1038 Impact Last Alert System, a pair of robotic telescopes in Hawaii designed to detect near-Earth objects. However, this object was not in Earth's immediate vicinity in a dangerous sense. It was flagged due to its unusual movement against the background stars. a motion suggesting it was not gravitationally bound to our solar system. As news spread through the astronomical community, major observatories began directing their instruments toward this visitor from afar. The James Webb Space Telescope observed 3IATLAS on August 6th, utilizing its near-spec instrument, the near-infrared spectrograph, capable of dissecting light into its constituent wavelengths to reveal composition. The Hubble Space Telescope captured images. Ground-based observatories worldwide contributed data during favorable weather conditions. Each observation added to the accumulating data set, and each observation confirmed that something unusual was occurring here, or more accurately, something unusual was not occurring. The anticipated cometary activity, which should have been prominently displayed, remained conspicuously absent, or at least invisible to our instruments. This is not a solitary observation from a single telescope on a single unfavorable night. We are witnessing consistent patterns across multiple instruments, various wavelengths, and numerous observation dates. The statistical significance of this anomaly grows with each new data point. This phenomenon is real, it is reproducible, and it demands an explanation. Therefore, as we transition to a detailed examination of this paradox, keep these figures in mind: 13% mass loss implied by acceleration versus virtually zero visible mass loss detected in images. Between these two facts lies a chasm that conventional cometary science is struggling to bridge. Part 3 explores the paradox in observational terms. It is essential to establish a benchmark to fully appreciate the degree of 3IATLAS's strangeness. The most effective method is to remind ourselves of what typical cometary behavior entails. You have likely seen images of renowned comets such as Halley's Comet with its brilliant double tail in 1997, or Comet McNaught, which produced a spectacular fan-shaped display in the southern hemisphere in 2007. These celestial bodies serve as textbook examples of what transpires when volatile, rich objects enter the inner solar system and begin to heat up under solar radiation. The process originates beneath the surface. A typical comet nucleus is often described as a dirty snowball, or more accurately, given the substantial dust content many possess, an icy dirt ball. The composition varies, but water ice is generally the predominant volatile, mixed with frozen carbon dioxide, carbon monoxide, methane, ammonia, and various organic compounds. All of these are bound together by silicate dust and occasionally larger rocky fragments. When solar heating penetrates the surface, these frozen volatiles absorb energy and sublimate. The resulting gas does not escape uniformly. Instead, it erupts through weak points in the surface, creating jets that can be remarkably focused. Imagine them as geysers on a cosmic scale. These gas jets carry dust particles with them, particles that can range in size from sub-micron grains to pebble-sized fragments. Once liberated from the nucleus, this material forms the coma, a diffuse envelope that can expand to a size larger than Jupiter. Despite the nucleus itself potentially being only a few miles in diameter, the gas in the coma fluoresces, meaning it absorbs ultraviolet light from the sun and re-emits it at visible wavelengths, producing that characteristic greenish or bluish glow. Meanwhile, the dust scatters sunlight, creating a yellowish or white reflection that makes the coma visible even from Earth. Then come the tails. Dust particles propelled by the sun's radiation pressure form a curved tail that follows the comet's orbital path. This tail often appears yellowish-white because it is simply reflecting sunlight off small particles. Simultaneously, the gas, ionized by solar radiation and the solar wind, is swept back along magnetic field lines, forming a straighter, bluer tail that points directly away from the sun. Many bright comets exhibit both tails distinctly, creating that classic two-tailed appearance that has terrified and fascinated humanity throughout recorded history. This is the established pattern. This is how volatile, rich comets behave when they approach the sun. The closer they get, the more active they become, until they eventually recede and the process reverses. We have observed this pattern hundreds of times with solar system comets. We witnessed it with Comet 2I Borisov, the previous interstellar comet visitor in 2019, which behaved precisely as anticipated, brightening, developing a coma, and displaying outgassing activity that perfectly aligned with conventional models. 3IATLAS experienced the same solar heating that would trigger this cascade of activity in any ordinary comet. It passed perihelion at 1.38 astronomical units, well within the range where water ice readily sublimates. It encountered recent solar storms that should have amplified activity, not suppressed it. And yet, when we examine high-resolution images from November 5, 2025, 1 week after perihelion, when activity should still be vigorous, we observe that star-like point source with no discernible coma, no visible tail, no diffuse envelope, essentially nothing. Let us return to the calculation of 13% mass loss as it represents the mathematical core of this paradox. If 3IATLAS lost 13% of its mass through gas ejection at 300 meters per second, which is what is necessary to explain the measured non-gravitational acceleration, then basic physics dictates what should happen to that gas and any dust it carries. The gas would expand rapidly, forming a cloud around the nucleus. Some of it would become ionized and swept away by the solar wind. Some would remain neutral and fluoresce under solar ultraviolet radiation. The dust would be pushed by radiation pressure, beginning to form a tail structure. Within hours to days, a visible coma would emerge. Within days to weeks, a developing tail would appear. There is no mechanism for losing such a significant amount of mass without creating an obvious visual signature, unless, of course, the ejected material possesses properties radically different from our expectations. Perhaps the gas is moving at a much higher velocity than 300 meters per second, dispersing too quickly to form a coherent coma. Perhaps the dust particles are so minuscule, sub-micron or even nanometer scale, that they are effectively invisible to optical telescopes, rapidly dispersed by radiation pressure or solar wind turbulence. Perhaps the outgassing is occurring in highly focused jets directed away from Earth, meaning we are observing the nucleus but not the expelled material. Alternatively, the surface might be exceptionally reflective or the dust extremely dark, preventing the usual scattering and fluorescence mechanisms from functioning as anticipated. These are all plausible avenues of consideration, and we will explore them in greater detail shortly. However, the uncomfortable truth is this. Each of these explanations necessitates the invocation of special circumstances, unusual conditions, or unconventional physics. Meanwhile, the most straightforward interpretation, one that requires no special pleading, is that 13% mass loss is simply not occurring. This in turn implies that the non-gravitational acceleration is not being caused by conventional outgassing, meaning we are observing something that deviates from our models of cometary behavior. Some researchers have highlighted the importance of detection thresholds. Modern telescopes are remarkably sensitive, but they are not infinitely so. Could the tail simply be too faint or too dispersed for us to detect? In principle, yes. However, we must be realistic about the limitations of this argument. The telescopes observing 3IATLAS include some of the most powerful instruments humanity has ever developed. They are capable of detecting extremely faint emissions, mapping diffuse structures, and isolating signals from noisy backgrounds. If a substantial dust tail or gas envelope were present, these instruments would undoubtedly detect it. The fact that they are not is highly significant. You might be thinking to yourself, perhaps this celestial body is simply inert. Could it be a depleted comet that long ago expelled all its volatile materials, leaving it with nothing more to offer? This line of reasoning would indeed account for the apparent lack of observable activity. However, it fails to explain the non-gravitational acceleration, which unequivocally points to something being expelled. Dormant comets do not exhibit non-gravitational acceleration. They strictly adhere to predictable ballistic paths. The object designated 3IATLAS is not behaving in such a manner. Consequently, we find ourselves in a quandary, confronted by conflicting evidence. The dynamics of its movement suggest activity, while its visual appearance indicates dormancy. Standard comet physics offers no way to reconcile these two disparate observations. Either our current comprehension is flawed, or this object possesses fundamental characteristics that set it apart from the comets we have previously studied. This leads us to the central question that will likely preoccupy the remainder of this inquiry. What category of object exhibits such peculiar behavior? What visitor from beyond the confines of our solar system could manifest acceleration without visible expulsion of mass? Could it brighten in specific light spectrums without developing a cometary atmosphere? Could it traverse its closest approach to the sun and endure solar disturbances without unleashing the spectacular phenomena we have come to anticipate? Part 4 delves into initial interpretations and the diverse perspectives within the scientific community. The scientific consensus on 3IATLAS is not monolithic, and this diversity of thought is precisely as it should be. What we are witnessing is the inherent messiness, the robust debate, and the self-correcting nature of scientific exploration as it grapples with observations that defy established paradigms. Different researchers examining the identical dataset arrive at divergent conclusions, each influenced by their specific expertise, presuppositions, and their readiness to consider unconventional hypotheses. Let us introduce some of the key individuals involved in this discussion, as understanding the spectrum of interpretations will be crucial for navigating the evidence. Stephen Burns, an observer who has diligently tracked 3IATLAS, has emerged as a proponent of what might be termed the radical reinterpretation camp. Burns asserts that the absence of visible gas and dust ejection is not a failure of detection or an issue with the timing of observations. Rather, it conveys fundamental information about the object's composition. If its passage through perihelion and exposure to solar storms were insufficient to energize this entity to the point of significant outgassing, then the deduction seems unavoidable. It lacks a substantial concentration of volatile compounds and dust to begin with. Burns has publicly declared his belief that 3IATLAS is essentially a solid mass of metal and carbon, bearing no resemblance to an icy comet. This interpretation possesses the advantage of simplicity. It accepts the observations at face value and proposes, look, if it doesn't behave like an icy comet, perhaps it isn't one. We might be dealing with an interstellar asteroid, a rocky or metallic body that was ejected from another star system and is now passing through ours. Such objects are theoretically expected to exist. Planetary formation is a turbulent process, and collisions or gravitational interactions are bound to regularly propel rocky and metallic fragments into interstellar space. Eventually, some of these fragments will inevitably find their way into other star systems. It would in fact be surprising if we never encountered such objects. However, this interpretation must still account for the observed non-gravitational acceleration. And this is where the matter becomes intricate. If the object is predominantly composed of metal and carbon with a minimal volatile content, from whence does the acceleration originate? Burns and others within this group might suggest that even a small quantity of volatiles, perhaps concentrated in discrete pockets beneath a heat-resistant outer layer, could generate propulsion without producing a visible coma. Alternatively, it is conceivable that the acceleration is not a result of outgassing at all, but stems from some other mechanism that is yet to be fully understood. On the opposing side of this debate stands researchers like Daryl Seligman, who contends that there is unequivocal evidence of cometary activity associated with 3IATLAS. Seligman's stance represents a more conservative viewpoint. He posits that this is indeed a comet exhibiting activity, and while its composition may be unusual, we should refrain from resorting to exotic explanations when conventional comet physics can still potentially account for the observed phenomena. It is possible that the dust particles are exceptionally small, rendering the coma and tail more difficult to detect. Perhaps the volatile content is lower than that of typical solar system comets, yet still sufficient to drive activity. It is also conceivable that we are observing a comet that has undergone significant alteration over billions of years in interstellar space, its surface modified by cosmic rays and interstellar dust impacts, to the extent that it no longer behaves like pristine cometary material. This interpretation is characterized by its conservatism. It does not necessitate the invention of new classifications or the invocation of processes that remain poorly understood. Comets can exhibit variability and can present surprises. The very fact that 3IATLAS is an interstellar visitor implies that we should anticipate some divergences from solar system comets, which originated within our specific protoplanetary disk under its unique compositional gradients. Different star systems may produce comets with distinct volatile compositions, varying ratios of dust to ice, and differing physical properties. The term unusual does not inherently imply non-cometary. However, this interpretation must also provide an explanation for why the evidence of activity remains so elusive. Why is the tail not visible? Why is the coma so faint or entirely absent in high-resolution imagery? The conservative camp offers potential explanations such as detection limitations, viewing geometry, or peculiar grain characteristics. Yet these explanations, when accumulated, begin to form a list of special circumstances that might lead one to question whether we are overly exerting ourselves to preserve the cometary interpretation when alternative possibilities warrant more open consideration. Then there is Avi Loeb, the Harvard astrophysicist, who has become a somewhat contentious figure in recent years due to his willingness to explore the possibility that certain astronomical anomalies might have artificial origins. Loeb views 3IATLAS through two primary lenses. Either it is an exceptionally unusual comet with properties previously unencountered, or it is a technological artifact, something manufactured by an intelligent entity, whether functional or defunct, now adrift in interstellar space. Loeb does not claim to definitively know which interpretation is correct. He simply argues that given the observed anomalies, we should be receptive to seriously investigating the technological hypothesis rather than dismissing it outright. This perspective is commendable for its intellectual honesty regarding the limitations of our current knowledge. We have identified only 3 confirmed interstellar objects to date. 1, Oumuamua in the year 2017, I, Borisov in 2019, and now 3IATLAS. This represents a sample size of 3. Drawing sweeping conclusions about the definitive nature of interstellar objects based on such a limited sample is epistemologically precarious. If we remain open to unexpected findings, we must at least entertain possibilities that appear improbable based on our restricted experience. And if we are considering possibilities, the hypothesis of a technological artifact warrants a place at the discussion table, not because it is probable, but because the repercussions of overlooking such a detection would be profound. However, this interpretation faces the substantial burden of requiring extraordinary evidence to substantiate extraordinary claims. The mere fact that an object is unusual does not automatically imply artificiality. The universe naturally generates a multitude of strange phenomena through natural processes. If we are to seriously entertain the notion that 3IATLAS might be a manufactured object, we require more than just anomalies. We need affirmative evidence of artificiality, such as geometric structures, narrow-band radio transmissions, or materials exhibiting impossible natural abundances. Anything that cannot be explained by any plausible natural formation or alteration process. To date, we lack such definitive proof. What we are observing is a fascinating social phenomenon intertwined with a scientific one. The narrative surrounding 3IATLAS is evolving in real time, transitioning from its initial perception as just another interstellar comet to something remarkably peculiar, with various factions establishing their positions along this spectrum. The media has amplified this tension, with some publications featuring sensational headlines about alien probes, while others maintain a stance of skeptical caution. The public is understandably seeking clarity. Should we be excited? Should we be skeptical? Are astronomers withholding information, or are they exercising appropriate prudence? The implications of this debate extend far beyond a single object. If 3IATLAS is merely an atypical comet, a natural body whose composition and behavior broaden our understanding of cometary diversity, that in itself is scientifically valuable and intriguing. We would learn that interstellar comets can differ significantly from their solar system counterparts, providing insights into planet formation conditions in other stellar systems. However, if it is something entirely different, whether a natural object belonging to a class we have not yet recognized or genuinely artificial, then the implications expand exponentially. We would be confronted with evidence that our existing categories are inadequate, our assumptions are limited, and the cosmos harbors surprises we have yet to even contemplate. And if one ventures into truly speculative territory, we might be witnessing the first detected piece of extraterrestrial technology, a discovery that would undoubtedly rank among the most significant in human history. One aspect appears certain: the debate is far from concluded, and further observations will be critical for its resolution. For now, keep this range of interpretations in mind, because as we delve deeper into the data, you will observe how different pieces of evidence seem to bolster or undermine each camp's position. Part 5. Setting the stage for the stakes involved. Before we embark on the detailed technical exploration that Act 2 will entail, it is imperative to pause and consider what is truly at stake here. Why does it matter whether 3IATLAS is classified as an unusual comet, a dense metallic and carbonaceous body, or something even more enigmatic? What difference does the definitive answer make to anyone beyond the select group of astronomers studying interstellar objects? The answer is that this is not merely an academic exercise. The ramifications extend across multiple fields of knowledge, from planetary science and astrobiology to the ongoing search for extraterrestrial intelligence. Furthermore, they touch upon fundamental questions regarding our place in a universe that we are only just beginning to comprehend. Let us commence with the most conservative scenario, the one that requires the fewest assumptions. 3IATLAS is a natural object, but it represents a novel type of comet or a class of small celestial body that has not been adequately recognized. Even this relatively modest conclusion would carry significant scientific weight. It would compel us to broaden our taxonomic systems, creating new categories for classifying both solar system and interstellar objects. Currently, we broadly categorize small bodies into comets, characterized by substantial volatile content and observable outgassing activity, and asteroids, which are primarily rocky or metallic and exhibit no such activity. However, nature does not always conform to our classifications. Certain objects blur these distinctions, such as the main belt comets that orbit within the asteroid belt but occasionally display cometary behavior. 3IATLAS might reveal that the spectrum of small body types is far wider than we have previously supposed, particularly when we consider objects that have formed in other stellar systems under different conditions. This expansion of our classification system has implications for our models of planet formation. When a protoplanetary disk collapses around a young star, the temperature gradient dictates what materials can condense and where. In close proximity to the star, where temperatures are too high for volatile ices, rocky and metallic materials are formed. Further out, beyond various ice lines, where different compounds can freeze, volatile, rich bodies begin to emerge. However, the precise details of this process, the exact temperatures, pressures, compositions, and timescales, vary from system to system. By studying interstellar visitors, we're essentially sampling the products of planet formation in other stellar systems. Each visitor acts as a messenger, conveying information about the conditions prevalent around other stars. If 3IATLAS informs us that some systems abundantly produce metallic and carbonaceous bodies, or that certain comets can lose their volatile constituents through prolonged exposure to interstellar conditions, this constitutes valuable data regarding planetary system diversity. The implications for astronomy extend even further. Our current understanding of cometary behavior is predominantly derived from observations of solar system comets, bodies that formed within our specific protoplanetary disk approximately 4.6 billion years ago. This constitutes a biased sample. These comets share similar ages, comparable formation conditions, and equivalent initial chemical compositions. Interstellar visitors disrupt this bias. They originate from systems of varying ages, metallicities, and formation histories. By studying them, we can begin to discern which properties of comets are universal and which are merely incidental to the history of our particular system. Now let us consider the implications for astrobiology, which might seem tangential until one recognizes that astrobiology fundamentally seeks to understand the distribution of life-supporting conditions throughout the universe. The composition of small bodies is relevant to astrobiology because these objects deliver volatiles and organic compounds to planets. Earth's water is likely largely a consequence of cometary bombardment during and after the planet's formation. Many of the organic molecules that served as the building blocks for life may have been delivered by comets and asteroids. If we discover that interstellar objects possess compositions vastly different from those of solar system bodies, perhaps richer in certain organic compounds or depleted in water, or carrying substances not found in local comets, this will inform us about the chemical diversity of planetary systems and the range of initial conditions conducive to potential biospheres. However, let us escalate to a more provocative scenario. What if 3IATLAS is not entirely natural in origin? What if the artificial hypothesis proposed by Avi Loeb and a few others holds even a kernel of truth? In that event, we're no longer discussing planetary science. We are engaging with the search for extraterrestrial intelligence, with techno-signatures, with the distinct possibility that humanity is not alone in the cosmos. This is where the stakes transition from being purely scientific to potentially existential. The search for extraterrestrial intelligence has historically concentrated on radio signals, predicated on the assumption that a technological civilization might deliberately emit such signals. However, a complementary approach involves the detection of artificial objects that may have been manufactured by other civilizations. If technological species are common throughout the galaxy, and if some develop interstellar travel or dispatch probes, then over billions of years, space should accumulate a population of artificial objects, functioning probes, defunct machinery, debris from ancient spacecraft. A minuscule fraction of these objects might purely by chance traverse other star systems. Discovering one would be an extraordinarily improbable event, but not impossible. 1Oumuamua, the first confirmed interstellar visitor in the year 2017, ignited precisely this kind of speculation. Its unusual, elongated form, its acceleration without visible outgassing, and its tumbling rotation were all features that led some researchers to ponder its potential artificiality. The majority of astronomers concluded that it was likely a natural object, a peculiar but explicable product of some formation or alteration process that we do not fully comprehend. However, the debate highlighted a significant point. We currently lack clear criteria for definitively distinguishing between artificial and natural objects at astronomical distances. If an interstellar probe or artifact were to pass through our solar system, would we even recognize it as artificial? What would be the telltale signs? 3IATLAS presents analogous questions, arguably in an even more acute form. If it exhibits acceleration without visible mass loss, possesses an unusual composition, and displays characteristics that do not readily fit into natural categories, these are precisely the kinds of anomalies one might anticipate from something manufactured. That does not, however, mean it is manufactured. Anomalies are not evidence of artificiality in themselves, but they are potentially worthy of more thorough investigation, employing multiple techniques and searching for positive signatures that would differentiate the artificial from the natural. The sociological and cultural dimensions of this debate are also significant. How does the scientific community approach anomalies that might potentially indicate intelligence? There exists a tension between maintaining appropriate skepticism and remaining open-minded, enough not to overlook something extraordinary. There is also the matter of communication. How do scientists discuss these possibilities publicly without either sensationalizing them or dismissing them reflexively? The history of ufology has rendered many scientists wary of anything that might be associated with extraterrestrials, even when the discussion is sober, evidence-based, and appropriately qualified. However, this cultural baggage can potentially obscure legitimate anomalies that warrant investigation. The window of opportunity here is fleeting and rapidly closing. 3IATLAS is receding from the sun at a velocity of approximately 33 kilometers per second. With each passing day, it travels further away, becomes fainter, and consequently more challenging to observe. Eventually, within a period of months to a couple of years, it will become too faint for even our most advanced telescopes to study in detail. It will then vanish back into interstellar space, and we will lose the opportunity to gather further data. This situation creates a sense of urgency. We have a limited time frame to direct our instruments toward this object, to acquire spectral data, to map its surface, and to search for any anomalies that might reveal its true nature. Once it has departed, we will be left with the data we have managed to collect, and we'll have to draw conclusions based on that finite data set. This urgency connects to a broader theme in contemporary astronomy. We are currently experiencing a golden age of discovery, a period when our instruments have finally attained sufficient power to detect a wide array of rare, peculiar, and unexpected phenomena. The Naves Observatory's legacy survey of space and time, once operational, will discover thousands of small bodies each night, including additional interstellar visitors. We will be inundated with unusual objects, each potentially offering new insights into the cosmos. However, this abundance of data also necessitates the development of more effective frameworks for determining which anomalies warrant intensive follow-up and which likely represent routine variations. 3IATLAS is helping us to refine these frameworks in real time. So this is our current predicament: a single object traversing our solar system, behaving in ways that defy expectations. Multiple interpretations exist, each carrying distinct implications, a narrow window for data acquisition before its permanent departure, and a growing realization that our conclusions regarding this visitor could fundamentally alter our understanding not only of comets, but also of the types of objects that traverse the space between stars, and whether some of these objects might indeed have creators. In Act 2, we will meticulously examine every peculiar detail, every anomaly, and every oddity that renders 3IATLAS so perplexing to explain. And you will discover just how deep this rabbit hole extends. Part 6, Cataloging the Detailed Anomalies. Let us systematically list the peculiar characteristics. What we are about to do is compile a systematic inventory of every unusual property exhibited by 3IATLAS, comparing each against what would be expected from a typical comet or asteroid. By the time we conclude, you will understand the basis for astronomers' profound puzzlement regarding this object. Each anomaly viewed in isolation might be explicable as a variation, a matter of chance, or the result of unusual but natural circumstances. However, when these anomalies are considered collectively, their cumulative impact becomes increasingly difficult to dismiss. This is the architecture of a mystery, not a single decisive piece of evidence, but a constellation of oddities that, together, demand an explanation. Anomaly number 1, the orbit itself. 3IATLAS is traversing a retrograde trajectory, meaning it is orbiting the sun in the opposite direction to the planets and the majority of solar system objects. Elliptical paths that travel in a direction opposite to the prevailing flow are not impossible for celestial bodies formed naturally. Certain comets with lengthy orbital periods exhibit this characteristic. However, for a visitor originating from beyond our solar system, such retrograde motion is particularly significant because it influences how we interpret the object's origins and its cosmic voyage. Even more remarkable is its orbital tilt relative to the ecliptic plane, which is essentially the flat disk delineated by Earth's orbit and roughly mirrored by all the planets. 3IATLAS maintains an orbit inclined by approximately 5 degrees to the ecliptic. While this might not seem substantial, consider this: interstellar entities arrive from arbitrary directions within three-dimensional space. The likelihood of one appearing on a trajectory so closely aligned with the plane of our solar system is about 0.2%. This translates to a 1 in 500 chance. While not an impossibility, it certainly warrants closer scrutiny. One might surmise that the dynamics of the galaxy could provide an explanation. Perhaps objects tend to congregate within the galactic disk, a region our solar system also inhabits. Consequently, approaches near the ecliptic might actually be more frequent than random probability would suggest. This is a plausible hypothesis and could account for some of the observed alignment. However, it doesn't entirely resolve the unusual nature of the situation, particularly when combined with other anomalies we are about to explore. Keep this particular detail in your mental records as we proceed. The second anomaly pertains to the estimations of its size and mass, derived from its luminosity and then assumed albedo, which is the measure of its surface reflectivity. Scientists have calculated that the nucleus of 3IATLAS is considerably larger than any previous interstellar visitors we've detected. One Oumuamua was estimated to be a few hundred meters across, possibly elongated but small. 2I Borisov was approximately 1 kilometer in diameter, which is quite typical for a cometary nucleus. 3IATLAS, depending on your assumptions regarding its albedo and shape, could be several kilometers in diameter. If it is composed of dense metallic and carbonaceous material, as some suggest, its mass could be substantial, potentially orders of magnitude, greater than that of Oumuamua or Borisov. Why is this important? Because larger objects are less common. The distribution of small bodies by size follows a pattern known as a power law, where there are numerous small objects and progressively fewer larger ones. If 3IATLAS is indeed large, this makes it statistically less probable as a chance visitor, though not impossible. Furthermore, it impacts our interpretation of the absence of visible gas and dust emission. A larger body with greater thermal inertia might retain internal heat differently, could possess a thicker, processed surface layer, and might respond to solar heating in a manner distinct from a smaller object. The third anomaly concerns its compositional signatures, and this is where the situation becomes truly perplexing. Observations have detected emissions from 3IATLAS that indicate the presence of nickel in the released gas. Nickel itself is not entirely absent from comets. Metallic elements can be found as minor constituents in cometary dust and can be released when heated. However, the proportion of nickel relative to other elements appears anomalous. Specifically, there are claims that the ratio of nickel to cyanide is significantly higher than what is observed in typical comets. Concurrently, water, which should be the primary volatile component in any standard comet, seems to be remarkably depleted. Some reports suggest a water content as low as approximately 4% by mass, in contrast to the 50% or more expected in a typical icy comet. To be clear regarding the uncertainties involved, these compositional measurements are challenging to obtain, and not all of them have undergone thorough peer review and confirmation. Assertions about specific compounds such as nickel tetracarbonyl, a highly toxic industrial chemical, have surfaced in some news reports but should be approached with caution until validated through rigorous spectroscopic analysis. Nevertheless, even if we adopt a conservative stance and simply acknowledge the existence of nickel emissions and depleted water, this combination is difficult to reconcile with conventional cometary models. Where did this object form in such a way that nickel is abundant and water is scarce? What processes could result in such a composition? The fourth anomaly relates to its polarization properties. When light interacts with particles and scatters, it can become polarized, meaning its electromagnetic waves vibrate preferentially in specific directions rather than randomly. By measuring the polarization of sunlight reflected off these particles, astronomers can infer information about their size, shape, and composition. 3IATLAS reportedly exhibits extreme negative polarization, indicating that the scattered light is polarized perpendicularly to what would be anticipated. This differs from known comets, which typically display positive polarization from dust scattering. Such extreme negative polarization suggests either highly unusual particle characteristics, such as metallic grains or exceptionally irregular shapes, or a combination of factors not typically encountered. Again, caution is warranted regarding certainty. Polarization measurements are technically demanding and contingent upon observational conditions. However, if this finding is substantiated, It points to a surface or surrounding particle cloud with properties that deviate from typical cometary dust. The fifth anomaly is its rapid brightening and color alteration as it neared perihelion. As 3I-ATLAS approached the Sun, its luminosity increased dramatically, a five-fold surge in green band flux as previously mentioned. However, the pattern of brightening and the associated color shift were unusual. The object appeared to shift towards bluer wavelengths near perihelion, which could signify alterations in surface properties or the emergence of different emission mechanisms. For a typical comet, brightening near perihelion is attributed to increased dust production and gas fluorescence, and one would expect specific color trends based on the properties of the dust grains and gas chemistry. The behavior of 3I-ATLAS does not precisely align with these expectations, suggesting either atypical variations in surface albedo or emission from substances not normally predominant in comets. The sixth anomaly brings us back to the central paradox: non-gravitational acceleration without corresponding visible ejecta. We have already addressed this, but it merits inclusion in this catalog as it is arguably the most perplexing feature. The observed acceleration is a tangible and significant phenomenon, just as the absence of a visible coma and tail is equally evident. Reconciling these two facts necessitates invoking either extremely unusual gas ejection velocities, infinitesimally fine dust that is undetectable, narrowly focused jets that elude our detection, or some entirely different explanation. None of these explanations on its own is entirely satisfactory. Now let us consider the probability. Each anomaly possesses some inherent probability of occurring naturally. A retrograde orbit aligned with the ecliptic has a 0.2% chance. An unusual composition with high nickel and low water content is difficult to quantify, but is certainly uncommon based on our sample of comets. Extreme negative polarization is rare. Acceleration without visible outgassing is very rare. When independent, unlikely events are combined, their probabilities are multiplied. If each anomaly has a 10% chance of occurring naturally, which is likely a generous estimate, and there are 5 independent anomalies, the probability of all 5 occurring together by chance is 0.1 raised to the power of 5, resulting in 0.001% or 1 chance in 100,000. Of course, these anomalies may not be independent. It is possible they are all manifestations of a single underlying characteristic. For instance, if the object is metal-rich, this could account for its composition, its polarization, the absence of a tail, and its peculiar thermal response simultaneously. In such a scenario, we should not multiply the probabilities because they are interconnected. However, even then, the question remains, why is this object metal-rich? How common are metal-rich interstellar bodies? Are we simply fortunate to have observed one, or is something else at play? The issue of data reliability looms over this entire discussion. Not every claimed anomaly carries equal weight of evidence. Some measurements originate from meticulously calibrated instruments utilizing established methodologies. For example, the orbital parameters provided by JPL are exceptionally robust. Other measurements are more provisional. Spectroscopic compositional claims can be influenced by assumptions regarding temperature, viewing geometry, and signal-to-noise ratios. As we discuss these anomalies, it is crucial to maintain a mental hierarchy of confidence. What we can state with certainty is that 3I-ATLAS is unusual. The precise extent of its unusualness and the specific nature of these deviations are still under determination. Here's a helpful thought experiment. Imagine you are tasked with designing an interstellar object from the ground up, aiming to make it as peculiar as possible while still appearing potentially natural. You would likely endow it with an unusual orbit, a peculiar composition, anomalous acceleration, and minimal observable activity. You would make it large enough to be detected, but small enough to remain mysterious. You would incorporate just enough anomalies to puzzle scientists, without crossing the threshold into obvious artificiality. 3I-ATLAS aligns with almost every aspect of this thought experiment, which is either a remarkable coincidence or an indication that something fundamental about our categorization system is flawed. As we move forward, the question becomes, how do we explain this convergence of oddities? Is there a unifying model, whether natural or otherwise, that can account for all the observed phenomena? Or are we compelled to acknowledge that some features remain genuinely enigmatic, at least until further data is acquired? Part 7. Compositional and Physical Models. We must now delve into concrete physical models, as vague speculation will not suffice. If 3IATLAS is as rich in metals and carbon as the evidence suggests, we need to understand the physical implications of this, how such an object might form, and what observable consequences it would entail. Let us begin by contrasting the properties of refractory materials with those of volatile ices, as this distinction is fundamental to comprehending why a metal-rich body would behave so differently from an icy comet. Refractory materials such as iron, nickel, silicate rocks, and carbon compounds like graphite are substances that remain solid even at very high temperatures. When exposed to solar radiation, they do not readily sublimate like water ice or frozen carbon dioxide. Instead, they conduct heat into their interiors, warming gradually, and can reach elevated temperatures without significant mass loss through vaporization. This results in markedly different thermal behavior. An icy comet responds to solar heating by sublimating volatile substances, a process that dissipates heat through the latent heat of phase transition. In contrast, a metal-rich object absorbs heat and its temperature rises until thermal radiation carries the energy away. The equilibrium temperature might actually be higher for the refractory object because evaporative cooling is absent. If 3IATLAS possesses a predominantly metallic and carbonaceous composition, this would immediately explain the lack of a visible tail. There is no dust to form a tail because very little volatile ice is sublimating to carry dust particles away from the surface. Any dust present is presumably embedded within the solid matrix and is only released if surface materials physically disrupted, perhaps by micrometeorite impacts or thermal stresses. The observed brightening might be due to the exposure of fresh, more reflective material as the surface erodes, or from changes in surface temperature affecting thermal emission in the infrared spectrum. However, where would such an object originate? What natural processes can produce metal-rich bodies in interstellar space? One possibility is that 3IATLAS is a fragment from a differentiated celestial body, such as a small planet or a large asteroid that underwent internal melting, leading to a separation into a metallic core and a rocky mantle. A catastrophic collision could shatter such a body, ejecting fragments into space. Some of these fragments would consist of core material, predominantly metal. Over time, exposure to cosmic rays and space weathering could alter the surface, potentially depositing carbon-rich compounds. Eventually, gravitational interactions with planets or close stellar passages could impart sufficient velocity to the fragment, allowing it to escape its home star system entirely. Billions of years later, it wanders into our solar system, a fossilized remnant of violent events in some ancient planetary system. This natural formation scenario is plausible. We are aware that differentiation occurs. We know that catastrophic collisions happen. We understand that bodies can be ejected into interstellar space. This model does not rely on exotic physics or unknown processes. It is conservative and aligns with our understanding of planetary system evolution. The primary question concerns statistical probability. How common are such objects? If metal-rich interstellar fragments are rare, then detecting one among our limited sample of 3 interstellar visitors might be a matter of luck. If they are common, then our solar system's cometary population is skewed and unrepresentative, which would be significant in itself. Now let us consider an alternative hypothesis that causes discomfort for many scientists, but persists nonetheless. This is the possibility that 3IATLAS is not entirely natural, but rather represents an artificial construct, or at the very least, something that has been modified by processes unrelated to natural astrophysical evolution. Before your skepticism sensors activate, and they should, as extraordinary claims demand extraordinary evidence, Let us examine what this hypothesis actually entails and what observational signatures it might predict. An artificial object optimized for interstellar travel would likely prioritize specific design features: low mass for easier acceleration, a high strength-to-weight ratio, and possibly a reflective surface to utilize radiation pressure. Minimal volatile content would be advantageous because volatiles add mass without contributing to structural integrity. If you were designing an interstellar probe or sail, you might construct it from lightweight metals, carbon composites, or thin films, avoiding water ice and other volatiles unless they served a specific purpose. The resulting object would be dense, refractory, and would exhibit minimal outgassing even when subjected to heat. Does this sound familiar? It should, as it describes 3IATLAS rather accurately: the absence of water, the presence of metals, and the lack of a dust tail. All these characteristics align with what one might expect from a manufactured object rather than a natural comet. The non-gravitational acceleration could be attributed to deliberate venting of stored propellant through narrow jets, or to radiation pressure acting on a large surface area structure, or to some mechanism we have not yet identified. The unusual orbit could be the result of deliberate navigation choices made long ago, though this quickly enters speculative territory. However, the crucial point is this: surface similarity to a hypothetical artificial object is not evidence of artificiality, it is merely consistency. To genuinely support the artificial hypothesis, we would require positive evidence that cannot be explained by natural means. For instance, if we detected structured radio emissions modulated in a way that could not occur naturally, that would constitute strong evidence. If we observed geometric shapes such as perfect spheres, cylinders, or regular polygons, that would be suggestive. If spectroscopy revealed materials with isotopic ratios impossible in nature, or alloys requiring smelting, that would be compelling. If we detected energy sources inconsistent with solar heating and radioactive decay, we would have to seriously consider artificiality. We possess none of these indicators. What we have is an object with unusual properties that do not fit comfortably within existing natural categories. This warrants further investigation, the deployment of additional instruments, and the application of multiple diagnostic techniques, but it is not proof of anything beyond the fact that our categories may need to be expanded. There is also an intermediate possibility worth considering. Perhaps 3IATLAS is natural, but has been profoundly altered by its extensive journey through interstellar space in ways that dramatically change its properties. A recent study has suggested that over billions of years, cosmic ray bombardment can modify ice structures down to depths of 15 to 20 meters. High-energy particles impact the surface, breaking molecular bonds, rearranging crystal structures, and creating new compounds through radiolysis. Over immense timescales, this processing could transform the outer layers of an icy body into something quite different. Perhaps it forms a refractory crust that seals in volatiles, or a chemically altered regolith with properties unlike anything observed in solar system bodies that have not undergone such prolonged exposure. This hypothesis of cosmic weathering is appealing because it bridges the natural and the anomalous. It posits that the object began as a normal comet but was transformed into something peculiar by billions of years of interstellar exposure. This alteration is natural, as cosmic rays are a known phenomenon, but the timescales involved are far longer than those experienced by solar system bodies. This could explain why 3IATLAS appears different from 2I Borisov, which might have been ejected more recently and thus undergone less processing. The observations from the James Webb Space Telescope on August 6th utilizing NIR spec should be particularly informative. Near-infrared spectroscopy can reveal the chemical composition of surface materials and any gas being released. If the spectra show typical cometary molecules, water, carbon monoxide, carbon dioxide, simple organic compounds, then the cosmic weathering model gains support. If instead we detect exotic compounds or anomalous abundance ratios that cannot be produced through known radiolysis processes, that would push us towards more unusual explanations. One aspect deserving attention is the absence of observed dust despite significant solar heating. If 3I-ATLAS has a metal-rich surface, it may simply not be producing dust because there is no dust to produce. Alternatively, the surface might be sealed by a fusion crust, not literal fusion in the sense of high-temperature melting, but rather a consolidated layer formed by micrometeorite impacts and radiation processing that binds surface particles into a coherent shell. Such a crust could insulate subsurface volatiles, preventing their escape even when heated. Eventually, thermal stresses might fracture the crust, leading to sudden outbursts, but between these events, the object would appear inactive. The challenge for any model is to simultaneously explain all the observations. The natural metal-rich fragment model accounts for composition and the absence of a tail, but struggles to explain the acceleration. The cosmic weathering model explains surface properties, but requires reconciliation with the claims of unusual composition. The artificial hypothesis is consistent with multiple features, but lacks direct evidence and relies on extraordinary assumptions. No model is perfect, which implies that we are either missing data, misinterpreting data, or the object genuinely represents something outside our current frameworks. What we can confidently state is that 3I-ATLAS is compelling us to reevaluate our understanding of what interstellar objects can be, how they form, how they evolve, and how we should categorize them. This endeavor is valuable regardless of which model ultimately proves to be correct. Part 8. Mechanism of acceleration and absence of tail. The paradox of acceleration warrants a dedicated examination because it lies at the core of this enigma. Let us quantify this and meticulously review what the measured non-gravitational acceleration signifies, what it implies about mass loss, and why the numerical data conflicts with the visual observations. This is where the discrepancy between motion and appearance becomes mathematically stark. The measured acceleration comprises two components, radial and transverse. The radial component, which is the acceleration along the line connecting the object to the sun, is approximately 1.1 times 10 to the power of -6 astronomical units per day squared. The sideways motion, the acceleration perpendicular to that trajectory, is approximately 3.7 times 10 to the -7th astronomical units per day squared. These figures appear abstract, so let us transform them into more relatable measures. 1 astronomical unit per day squared equates to roughly 169 meters per second squared. Consequently, the acceleration directed towards or away from the sun is approximately 0.00186 meters per second squared. This is minuscule, about 20,000 times less potent than Earth's gravitational pull at its surface. Nevertheless, it is genuine, detectable, and necessitates an explanation. In typical comets, acceleration not attributable to gravity stems from a propulsive mechanism. Gases sublimate from the surface, are expelled outward at high speed, and in doing so impart a reactive force upon the comet's core. This is a direct application of Newton's third law of motion. The magnitude of this force is contingent upon the velocity of the expelled gas and the rate at which mass is ejected. For cometary gases sublimating from water ice, typical velocities range from 300 to 1,000 meters per second, influenced by temperature and the specific configuration of the outgassing process. Let us adopt 300 meters per second as a conservative estimate. We can now proceed with the calculation. Knowing the acceleration and the expulsion velocity allows us to work backward and determine the rate of mass depletion required to generate such acceleration. The relevant formula is quite straightforward. Acceleration equals the mass loss rate multiplied by the expulsion velocity, all divided by the object's total mass. Rearranging this equation yields mass loss rate equals acceleration multiplied by mass divided by the expulsion velocity. Substituting our figures and assuming a mass derived from estimations of its size and density, we arrive at a mass loss rate that, when integrated over the observation period from its closest approach to the sun through early November, amounts to approximately 13% of the object's total mass. 13%. Let that sink in. If 3IATLAS shed 13% of its mass through gas expulsion over a period of a few weeks, that constitutes significant activity, not subtle effervescence. That signifies vigorous outgassing comparable to that of highly active comets in the vicinity of their perihelion. The expelled gas alone would generate a substantial coma. The dust entrained within that gas, even if it represents a small fraction of the gas's mass, would scatter sunlight, creating visible structural features. It would be impossible to conceal such a substantial mass loss if one were trying. However, we're not observing this phenomenon. The images captured on November 5th depict a star-like point source. High-resolution observations reveal a minimal coma, no discernible tail structure, the dust that ought to be present, the gaseous envelope that should be there in essence. The entire visible manifestation of active mass loss is absent or, at the very least, significantly fainter than simple calculations would predict. Therefore, there must be an error in our calculations. Let us scrutinize the underlying assumptions. Firstly, the ejection velocity. It is possible that the gas is not moving at 300 meters per second. Perhaps it is traveling much faster. If the ejection velocity were 10 times greater, amounting to 3,000 meters per second, then only 1/10 of the mass loss would be necessary to produce the same acceleration, reducing the figure from 13% to approximately 1.3%. While still substantial, this is more readily concealed. But how could gas attain such a velocity of 3,000 meters per second? That speed approaches the escape velocity from Mars. For gas to achieve such speed, it would require either an exceptionally high temperature, measured in thousands of Kelvin, or acceleration by means other than thermal pressure. Neither of these scenarios aligns comfortably with our current understanding of cometary physics. The second assumption concerns the dust-to-gas ratio. It is conceivable that this ratio is exceptionally low. Typical comets eject a composite material of gas and dust, with dust frequently constituting a significant portion of the expelled mass. This dust is the very component responsible for generating the visible tail. If 3IATLAS is primarily ejecting gas with minimal dust content, the coma and tail would appear considerably fainter and be more challenging to detect. But what could account for such a disparity in the dust-to-gas ratio compared to conventional comets? Perhaps the composition is fundamentally different if the object is metal-rich with a scarcity of friable material. In such a case, there simply wouldn't be sufficient dust available for ejection. Alternatively, it is possible that the dust particles are exceptionally minute, sub-micron in size, and are immediately dispersed by radiation pressure, scattering too rapidly to form any cohesive structure. Furthermore, smaller particles are less effective at scattering light, rendering them more difficult to observe. The third potential scenario posits that the gas is being expelled in highly collimated jets rather than emanating as isotropic fountains. If outgassing occurs through narrow fissures or vents, creating focused beams of expelled material rather than diffuse sprays, then a considerable portion of the gas and dust might be ejected in directions away from Earth. In this situation, we would observe the nucleus, but not the ejected material. Certain comets do exhibit collimated jets observable in high-resolution imagery as narrow rays extending from the nucleus. However, even these focused jets eventually disperse, forming a broader coma at greater distances. Concealing all ejected material solely through jet geometry presents a significant challenge. The fourth possibility relates to radiation pressure or solar sail effects. If 3IATLAS possesses a very low mass relative to its size, perhaps it is configured as a thin sheet or has a highly porous structure, then radiation pressure from sunlight could induce acceleration without any accompanying mass ejection. Photons carrying momentum impart a force upon reflecting from a surface. For the majority of comets and asteroids, this force is negligible compared to their mass. However, for an object with sufficiently low mass and a substantial cross-sectional area, radiation pressure can become a significant factor. This was one of the proposed explanations for the acceleration observed in Oumuamua. The difficulty with this hypothesis is that achieving the requisite mass-to-area ratio necessitates either implausibly low densities or an implausibly vast surface area. A solid metallic object would not suffice. One would require something akin to a thin sail. The fifth option, and this leads us into more speculative territory, is that the acceleration is not a result of natural processes at all. If 3IATLAS were an artificial construct possessing internal mechanisms for generating thrust, then the acceleration could originate from the controlled expulsion of stored propellant, from some form of photon drive, from electromagnetic interactions with the solar wind, or from mechanisms yet unimagined. The crucial point is that artificial systems are capable of producing thrust without generating visible plumes. A contemporary spacecraft utilizing electric propulsion, for instance, produces an almost imperceptible exhaust. An ion drive expels particles at such high velocities and in such minute quantities that the exhaust plume is virtually transparent. It is imperative to be unequivocally clear. Invoking artificial mechanisms should not be undertaken lightly. It represents an explanation of last resort, to be considered only after all natural possibilities have been thoroughly exhausted. However, intellectual integrity demands acknowledging that if we remain genuinely perplexed by the acceleration mechanism, and if no natural explanations fit comfortably, then we should not categorically dismiss alternatives simply because they are uncomfortable or improbable. Scientific advancement is predicated on the consideration of all possibilities and the judicious weighing of evidence, not on the imposition of ideological boundaries around acceptable hypotheses. Part 10. Observational timing, solar context, and environment. The precise timing of our observations is of immense importance. To comprehend why 3IATLAS presents such a puzzle, we must examine the environmental context within which it traversed the inner solar system. This extends beyond mere geographical location or temperature fluctuations. It encompasses the entire ecosystem of radiation, particles, and forces that should have stimulated activity if this were a typical comet rich in volatiles. The fact that we did not observe such activity, despite ideal triggering conditions, deepens the mystery. Let us establish the precise scene. 3IATLAS reached its perihelion on October 29, 2025, at a distance of approximately 1.38 astronomical units from the Sun. This translates to roughly 128 million miles, positioning it comfortably between Earth's orbit at 1 astronomical unit and Mars's orbit at 1.5 astronomical units. For perspective, this distance falls well within what astronomers refer to as the water-ice sublimation zone. At this proximity, solar heating is sufficiently intense to vaporize water ice from a comet's surface at a robust rate. We are not discussing extreme closeness as with sun-grazing comets that plunge within a few solar radii and are entirely incinerated. This represents a relatively moderate heating environment where conventional cometary activity should proceed with steady predictability. The thermal input at 1.38 astronomical units is substantial. The solar constant at Earth's distance is approximately 1,360 watts per square meter. At 3IATLAS's perihelion distance, it is receiving roughly 700 watts per square meter of solar radiation. This is akin to directing multiple heat lamps at each square meter of the object's sunlit surface, hour after hour, day after day. Any water ice exposed to such a flux will sublimate. Carbon dioxide ice, which vaporizes at even lower temperatures than water, should be vigorously escaping. Frozen carbon monoxide, ammonia, methane, all the usual cometary volatiles, ought to be transitioning from solid to gaseous states and dispersing into space. However, solar heating is only one facet of the environmental narrative. The sun is not merely a static source of heat, it is a dynamic, volatile plasmasphere that frequently unleashes solar storms, coronal mass ejections, and energetic particle events. During the period surrounding 3IATLAS's perihelion passage, the sun was exhibiting heightened activity. Solar storms propagate shock waves of charged particles outward through the solar system at speeds ranging from hundreds to thousands of kilometers per second. These particles carry energy. Upon impacting a cometary surface, they can induce further heating, sputter material from the surface, impart electrical charges to dust grains, and generally amplify activity. The solar wind itself, the continuous stream of protons and electrons flowing from the sun at all times, intensifies as one approaches the sun. At one point, 3.8 astronomical units, 3IATLAS, was enveloped in a solar wind with a density and velocity that should have interacted strongly with any outgassing. The solar wind ionizes gas, stripping electrons from molecules and generating the glowing ion tail characteristic of active comets. It also exerts pressure on cometary material, contributing to the shaping and extension of tails. The confluence of thermal input, particle bombardment, and electromagnetic interactions should have created ideal conditions for cometary activity. Yet we observed virtually nothing. The images acquired on November 5th, 1 week after perihelion, reveal a star-like point. This timing is crucial because cometary activity does not cease instantaneously upon an object's passage through perihelion. The nucleus retains residual heat. Subsurface ice continues to sublimate. Jets persist in their expulsion. Activity typically remains elevated for days to weeks following perihelion before gradually diminishing as the comet recedes and cools. We should have been observing 3IATLAS during its period of peak activity when any present volatiles would still be enthusiastically venting. So, what could account for the absence of visible activity despite these favorable conditions? One possibility involves the concept of a refractory crust or mantle. Comets can develop an insulating layer on their surfaces over extended periods. If the nucleus has been traversing interstellar space for millions or billions of years, its surface may have undergone alterations due to cosmic ray exposure, forming a hardened shell. Recent research has specifically investigated this scenario for 3IATLAS. A study published in 2025 examined the effects of cosmic rays, high-energy particles prevalent throughout the galaxy, on an icy body during a prolonged interstellar journey. The findings were illuminating. Cosmic rays penetrate cometary ice, disrupting molecular bonds and initiating chemical reactions. Over millions of years, this process can modify the ice down to depths of 15 to 20 meters, creating what is essentially a processed, compacted layer quite distinct from pristine ice. This cosmically gardened material might exhibit reduced porosity, be less susceptible to rapid sublimation, and generally possess greater refractory properties than fresh cometary ice. If 3IATLAS possesses such a layer, it could function as an insulating blanket, trapping volatiles beneath and allowing only minimal outgassing, even under intense solar heating. But does this fully explain our observations? An insulating crust might delay or diminish activity. However, if substantial volatiles are present beneath the surface, that crust should eventually fracture. Thermal stresses, pressure buildup from subsurface sublimation, and the sheer intensity of perihelion heating should, in some locations, crack the surface, permitting gas to escape through vents or jets. We observed this phenomenon with solar system comets that develop crusty mantles. These do not completely suppress activity. They merely render it more episodic and localized. 3IATLAS appears to be suppressing activity far more effectively than a simple crust model would suggest. Another environmental consideration pertains to solar proximity in the history of heating. If 3IATLAS had previously passed in close proximity to another star during its interstellar journey, perhaps its original star billions of years ago, or another star encountered along its path, it might have already shed its most volatile surface materials. The object we are currently observing could be thermally processed, with only deeply situated or refractory volatiles remaining. These deep-seated volatiles might be venting at a slow rate, producing the measured acceleration without generating a visible coma because the mass loss rate is too low to accumulate a substantial cloud of dust and gas. The viewing geometry also plays a role. Although this explanation has limitations, it is conceivable that the outgassing jets are highly directional, pointing away from Earth or along our line of sight, thus obscuring the resultant coma and tail structures. It is possible that the dust is being ejected at angles that render it invisible to our telescopes. However, this requires a rather contrived geometric arrangement and does not account for the complete absence of any diffuse glow surrounding the nucleus in high-resolution imagery. Solar conjunction presents another timing challenge. During certain orbital phases, the object might have been too close to the sun in the sky for ground-based telescopes to observe effectively, being blinded by solar glare. Initial observations might have missed critical episodes of activity. Nevertheless, space-based telescopes such as Hubble and James Webb do not face the same constraints and have been tracking this object through multiple observation windows. The fact that they also report minimal activity suggests that the issue is not solely related to observational timing. There is also the possibility that solar storms did not enhance activity. Rather, they suppressed it or eliminated evidence of it. This may seem counterintuitive, but bear with us. If 3IATLAS was generating a very tenuous dust envelope, just barely detectable, intense fluxes of particles from solar storms might have swept that dust away more rapidly than usual, preventing the accumulation of a visible coma. Alternatively, the storms might have imparted such a strong electrical charge to the dust grains that electrostatic repulsion dispersed them quickly, again hindering buildup. While speculative, this illustrates that the solar environment is complex, and interactions may not always yield simple, predictable outcomes. The material properties of a metallic and carbon-rich body respond differently to solar heating compared to icy bodies. Metals possess high thermal conductivity. They readily absorb heat but also conduct it into their interior rather than concentrating it at the surface where sublimation occurs. A metallic surface might attain high temperatures without necessarily causing rapid expulsion of trapped volatiles from beneath. Metals also exhibit high reflectivity at specific wavelengths. If the surface is lustrous, perhaps metallic nickel or iron reflecting sunlight, it might not absorb as much thermal energy as a dark cometary surface would. This could reduce heating efficiency and slow down sublimation rates. Carbon-rich materials offer another perspective. Comets contain carbonaceous compounds. However, if 3IATLAS is unusually dominated by carbon, perhaps resembling carbonaceous chondrite meteorites, or even graphite in certain areas, its thermal characteristics would differ significantly from typical mixtures of ice and dust. Carbon exhibits high thermal stability. It does not sublimate at temperatures relevant to the inner solar system. A carbon-rich object might simply absorb solar heat and re-radiate it into space without producing significant outgassing. All these environmental and material considerations converge on a single conclusion. 3IATLAS is not reacting to its environment in the manner expected of a typical comet rich in volatiles. Whether this is due to prolonged processing during interstellar transit and unusual bulk composition, protective surface layers, or a combination of factors, the object appears resistant to the usual triggers that would result in spectacular cometary activity. And it is precisely this resistance that makes it so fascinating and so challenging to categorize. In the subsequent section, we will explore how the scientific community and the broader culture are confronting this anomaly and the sometimes uncomfortable tensions that arise when observations deviate from expectations. Part 11. Controversies, institutional responses, and conspiracies. Scientific inquiry does not occur in isolation, and the narrative of 3IATLAS is as much about the way institutions, researchers, and the public react to anomalies as it is about the anomalies themselves. There is a fascinating sociology to this mystery, a drama unfolding across academic papers, press releases, social media discussions, and informal conversations among astronomers. Understanding these dynamics helps us discern why certain interpretations gain traction while others are dismissed, and why the process of making sense of peculiar observations can be slower and more convoluted than we might anticipate. The scientific establishment, including entities like NASA, the European Space Agency, major universities, and professional astronomy organizations, operates on principles of caution and peer review. This is generally a strength, as it prevents premature announcements, filters out observational errors and hasty interpretations. and upholds credibility by ensuring claims are adequately substantiated before public dissemination. However, it also engenders institutional inertia. Organizations tend to be risk-averse, particularly when confronted with extraordinary claims. Proposing that an astronomical object might be artificial, even tentatively, carries immense reputational risk. If one is mistaken, they become the individual who raised a false alarm about alien probes, having wasted everyone's time. If, however, they are correct, well, that outcome seems so improbable that the risk is scarcely worth taking. This cultivates an asymmetric incentive structure. There is very little potential benefit and enormous potential detriment associated with being the first major institution to suggest that 3IATLAS might be artificial. It is far more prudent to adhere to conventional explanations, to emphasize the need for further data, and to frame the object as unusual but likely natural. And frankly, this is probably the correct stance in most circumstances. Anomalies typically resolve into prosaic explanations once they are better understood. The history of astronomy is replete with mysteries that dissolved under scrutiny. Pulsars, initially thought to be alien beacons, now understood as rapidly rotating neutron stars. Fast radio bursts, which seemed inexplicable, are now recognized as natural cosmic phenomena. However, this caution can sometimes border on excessive conservatism, a reluctance to seriously investigate possibilities that, while seemingly unlikely, are not impossible. We witnessed this tension manifest dramatically with Oumuamua, when that object exhibited non-gravitational acceleration and an unusually elongated shape. Avi Loeb raised the question of whether it might be artificial, specifically proposing it could be a light sail, a large, thin sheet propelled by starlight. The majority of astronomers rejected this hypothesis, arguing that natural explanations were more plausible. A cometary outgassing explanation was eventually developed and gained acceptance, although not without some lingering questions. 3IATLAS has reignited similar debates, but with arguably more compelling evidence. The combination of acceleration without visible outgassing and unusual composition and multiple other anomalies renders the natural explanations less comfortable than they were for Oumuamua. This has resulted in a fractured landscape of opinion. A contingent of academics openly postulates that this particular entity might defy all established natural classifications. Conversely, others steadfastly adhere to conventional cometary explanations, asserting that we are merely observing typical variability magnified by insufficient data. A select few are prepared to voice in public what many contemplate in private, that we should at the very least rigorously explore the possibility of this object being artificial. The media's role in this unfolding narrative is multifaceted. Science journalism navigates a precarious path, balancing the accurate representation of uncertainty with the provision of concrete takeaways for the readership. Headlines touting alien probes or enigmatic interstellar entities garner significant engagement and readership. Simultaneously, they risk misinforming the public regarding the true evidentiary status. Certain publications have embraced sensationalism, presenting narratives that strongly suggest Oumuamua could be artificial while minimizing the numerous disclaimers and ambiguities. Other news sources have adopted a more tempered approach, highlighting peculiarities while stressing that natural explanations remain entirely plausible. This disparity cultivates confusion among an interested public. For individuals not deeply immersed in the astronomical community, discerning well-supported claims from speculative ones proves challenging. Are the observed nickel emissions genuine? Do they represent the degree of anomaly some reports suggest? The reality is that some of the most compelling assertions regarding Oumuamua have yet to undergo comprehensive peer review. Reports of nickel tetracarbonyl detection, that volatile nickel compound I previously mentioned, have appeared in outlets such as Newsweek and the New York Post. These are not scientific journals. They are disseminating information based on preliminary observations or unofficial statements that have not been subjected to the rigorous scrutiny of peer review. This situation underscores a significant challenge in contemporary scientific communication. The conventional research timeline, making an observation, analyzing the data, composing a paper, submitting it for peer review, enduring months of revisions and waiting for publication, and then announcing the findings, is simply too protracted for the internet era. By the time a scientific paper is officially published, the subject matter has already been extensively discussed, deconstructed, and debated across social media platforms and popular science publications. Researchers often feel compelled to comment publicly on ongoing work, leading to a proliferation of preliminary findings that may not withstand closer scrutiny. We must also address conspiracy-adjacent interpretations, as they are prevalent and significantly shape public perception of this object. Certain internet communities have seized upon Oumuamua as evidence of governmental concealment, suppressed extraterrestrial contact, or other conspiratorial theories. These interpretations typically hinge on the premise that authorities possess undisclosed knowledge, and that definitive proof of artificiality is being deliberately withheld from the public. This is almost certainly not the case. The astronomical community is vast, international, and highly competitive. Were there irrefutable evidence that Oumuamua was artificial, its suppression would be virtually impossible. Someone would inevitably publish, someone would leak the information, and someone would eagerly claim credit for the century's most profound discovery. The more prosaic truth is that we simply do not know yet. We are faced with anomalies lacking clear explanations. We have competing hypotheses, none of which perfectly reconcile all the gathered data. We observe institutional prudence conflicting with the willingness of individual researchers to speculate. Furthermore, we have a limited temporal window for gathering additional observations before the object becomes too faint for effective study. This situation generates frustration across all parties involved. Researchers are frustrated by restricted telescope access and incomplete data sets. Institutions are frustrated by the pressure to issue pronouncements before conclusive evidence is available, and the general public is frustrated by science's apparent inability to provide a definitive answer. There is also an ethical dimension to how we communicate about such objects. If we prematurely leap to conclusions of potential artificiality, we risk issuing false alarms, thereby eroding public trust in astronomical pronouncements. When the next truly extraordinary discovery emerges, will it be met with skepticism? Conversely, if we are overly dismissive of anomalies, too quick to shoehorn observations into conventional frameworks, we might overlook something genuinely revolutionary. Striking the right balance, fostering open-minded skepticism, conducting rigorous investigations, and communicating uncertainty honestly is far easier in theory than in practice. The question of resource allocation is also pertinent. Telescope time is a scarce and highly sought-after commodity. Every hour dedicated to observing Oumuamua means foregoing observations for other scientific endeavors, characterizing exoplanets, surveying distant galaxies, tracking near-Earth asteroids, and a host of other research projects that compete for the same instruments. This creates pressure to justify why this particular object warrants intensive follow-up. If it is likely just an unusual comet, perhaps resources would be better directed elsewhere. However, if there exists even a minuscule chance of something more significant, the potential scientific return could justify the investment. These are complex judgments with no clear-cut correct answers. What transpires if Oumuamua ultimately proves to be an eccentric but natural comet, and we have spent months engaging in speculation about artificial origins? Some will contend that time and credibility were wasted. Others will argue that the process of seriously investigating the possibility was valuable, that we refined our criteria for differentiating between natural and artificial phenomena, and that we expanded the scope of questions we're willing to pose. Both viewpoints hold merit. And what if, and I wish to emphasize this, which remains a significant hypothetical, what if there is substance to the artificial hypothesis? What if subsequent observations reveal unmistakable indicators of manufacturing, of engineering, of deliberate construction? The repercussions would permeate every facet of human knowledge. We would possess empirical confirmation of intelligence existing or having existed elsewhere in the galaxy. We would have tangible evidence extending beyond mere radio signals. We might even gain access to materials and technologies developed under profoundly different evolutionary and cultural circumstances. The scientific, philosophical, and cultural ramifications would be immense, difficult to fully comprehend. However, we have not yet reached that juncture. What we currently possess is enigma, discord, incomplete data, and the ponderous methodical machinery of science striving to interpret observations that deviate from our expectations. In the subsequent section, we'll broaden our perspective beyond this specific object to examine its place within the larger trends in astronomy and space science during the year 2025. This is because Oumuamua is not the sole discovery challenging our assumptions this year. Part 11, Recent Discovery, Exoplanet Super-Venus Revisited. While our attention has been captivated by Oumuamua traversing our solar system, astronomers studying exoplanets, planets orbiting distant stars, have been confronting their own category-defying surprises. One recent revelation from 2025 exemplifies how our preconceptions regarding planetary composition and formation are being challenged on multiple fronts. The narrative surrounding a newly characterized super-Venus offers a pertinent parallel to our interstellar visitor, suggesting that peculiarity might be more widespread in the cosmos than we initially presumed. The celestial body in question orbits a star located approximately 150 light-years from Earth. Initial assessments indicated it resembled Venus, possessing a similar size and orbital distance from its star, presumably a comparable composition, a terrestrial world potentially shrouded in a dense atmosphere and scorched by its stellar proximity. Analogues to Venus are significant because they enhance our understanding of planetary climate and habitability. Venus within our own solar system is a desolate inferno, with surface temperatures capable of melting lead and atmospheric pressures 90 times that of Earth. However, it may not have always been so. Comprehending the evolutionary trajectories of Venus-like worlds aids in contemplating the spectrum of planetary outcomes and the factors that render a planet habitable versus inhospitable. Consequently, astronomers directed powerful instruments toward this distant Venus analog, anticipating confirmation of their existing models. They meticulously measured its transit, the slight diminution in starlight as the planet crosses in front of its star, with exceptional precision. They analyzed the starlight that filtered through the planet's atmosphere during these transits, searching for spectroscopic signatures indicative of atmospheric composition. They determined the planet's mass by detecting the minute gravitational perturbation it exerts on its star's motion. Upon synthesizing all the data, a discrepancy emerged. The planet's density was considerably higher than anticipated, significantly so. Venus exhibits a density of approximately 5.2 grams per cubic centimeter, consistent with a rocky, iron-cored celestial body. This super-Venus registered a notably greater value, suggesting a composition richer in heavier elements, more iron, perhaps substantial quantities of nickel or other dense metals, and potentially less of the lighter silicate rock that constitutes planetary mantles. It was as if a standard rocky planet had been fundamentally altered, with considerable portions of its rocky material replaced by metal. This immediately raises questions for planetary formation theories. Rocky planets are formed through accretion, where dust and smaller bodies within a protoplanetary disk collide and adhere, gradually coalescing into larger entities. The elemental makeup of these planets is contingent upon the materials available in the specific region of the disk where they originated. In proximity to the star, temperatures are elevated, favoring materials with high condensation points, such as metals and refractory minerals. Further out, one encounters volatile ices and organic compounds. This establishes a gradient in composition across the planetary system. However, this super-Venus appears to contravene these expectations. At its orbital distance, such a metal-rich composition would not be expected unless an unusual event occurred. Perhaps the planet formed at a greater distance and migrated inward, although this does not definitively account for the elevated metal content. Possibly a colossal impact event stripped away lighter mantle material, leaving behind a disproportionately large metallic core. Alternatively, the protoplanetary disk itself may have possessed an anomalous composition from its inception, being richer in metals than typical disks. Each of these explanations necessitates exceptional circumstances, and none is entirely satisfactory. Does this sound familiar? We are encountering a similar pattern with Oumuamua observations that do not align with established models, a composition that seems incongruous with the prevailing conditions, and a requirement to invoke specialized formation or alteration processes to reconcile the observations. The parallel is instructive. It suggests we may be systematically underestimating the diversity of outcomes possible in planetary system formation. Consider the implications for our understanding of smaller celestial bodies like comets and asteroids. If planets can exhibit widely divergent compositions even at similar orbital distances across different systems, then the smaller bodies within those systems, the residual material from planet formation, should display comparable variability. An interstellar object ejected from a metal-rich planetary system might bear no resemblance to the ice and rock comets familiar to us from our solar system. It could be predominantly metallic or carbonaceous, with minimal volatiles reflecting the abundance of materials in its birth environment. This reframes Oumuamua in an intriguing light. Perhaps it is not defying the established behaviors of comets. Instead, it might be adhering to principles from a different planetary system, one where the raw materials for small body formation differed significantly from our own. Our solar system originated from a protoplanetary disk with a specific metallicity, a particular carbon-to-oxygen ratio, and distinct temperature gradients and dynamical evolution. Other systems formed under different conditions, and consequently, their comets and asteroids might possess divergent typical compositions. The discovery of the super-Venus also underscores the limitations of our exoplanet sample size. We have now characterized thousands, although the majority are large gas giants or super-Earths, which are easier to detect. We're only beginning to thoroughly characterize the composition of rocky planets. Each new measurement reveals surprising diversity. Regarding interstellar objects, we have confirmed the arrival of precisely 3 visitors. This hardly constitutes a representative sample. It is barely sufficient to establish the existence of interstellar objects. Drawing definitive conclusions about what is normal versus anomalous based on 3 examples is epistemologically precarious. Consider this thought experiment. Imagine an extraterrestrial civilization that has studied the small bodies within their solar system for centuries. They have observed thousands of comets and asteroids, all originating from their local protoplanetary disk. They have developed models defining what comets are, how they behave, and their constituent materials. Then, an interstellar visitor arrives from our solar system, let's say a Jupiter family comet. By our standards, it is typical. To them, it might appear utterly peculiar. Its ice composition would be incorrect, its rock-to-ice ratio anomalous, and it might contain strange organic molecules unseen in their local comets. They might debate whether it is even a comet or belongs to a different class of object. The fundamental point is that normal is defined by one's local sample, and the universe may not adhere to these local definitions. This does not resolve the mystery of Oumuamua, but it provides context. We're living through a period where multiple discoveries across various astronomical fields are challenging our established assumptions. Planets are not as standardized as we once believed. Small bodies, it appears, are also subject to this variability. The cosmos exhibits greater variety and a more inventive approach to its construction than our models had anticipated. This is simultaneously humbling and exhilarating. It signifies that there is more to discover, more categories to map, and more physical regimes to explore. It also implies that we must exercise caution in dismissing anomalies too readily. When confronted with something that deviates from our established frameworks, whether it be a super-dense Venus analog or a comet exhibiting acceleration without outgassing, our initial inclination is often to force it into the nearest available category or to invoke specific circumstances to preserve our existing models. However, at times the appropriate response is to genuinely consider that our categories might be incomplete, and that the universe harbors phenomena we have yet to adequately conceptualize. The history of science is replete with instances where anomalies precipitated paradigm shifts. Mercury's orbital precession revealed general relativity, the spectrum of black body radiation illuminated quantum mechanics, and the rotation curves of galaxies pointed to the existence of dark matter. Not every anomaly leads to a revolution, but those that do are instrumental in the advancement of knowledge. Therefore, as we continue our investigation of Oumuamua, let us bear this broader context in mind. We are not merely studying a single anomalous object. We are probing the boundaries of our understanding across the board, from planetary composition to the physics of small bodies to the diverse outcomes of planetary system formation. Each observation reveals a universe that is vaster, more mysterious, and more varied than we had imagined. Part 12. AI, Augmented Asteroid, and Comet Detection and Classification. The deluge of data in contemporary astronomy presents both an opportunity and a crisis. The opportunity arises from our unprecedented ability to observe the cosmos with remarkable depth, temporal coverage, and across a wide range of wavelengths. The crisis stems from the sheer volume of data, which far exceeds humanity's capacity for analysis. This is where artificial intelligence enters the narrative, and it is particularly relevant to objects like Oumuamua, which represent rare anomalous phenomena easily obscured by the noise of routine observations. Understanding how artificial intelligence is transforming the field of small body astronomy enhances our appreciation of both what we are discovering and what we might be overlooking. Let us begin by considering the scale of the challenge. Traditional astronomical surveys captured perhaps thousands of images per night, with each image containing hundreds to thousands of objects, stars, galaxies, asteroids, and artifacts. Human astronomers or small teams could review these images, flagging interesting objects for subsequent investigation. However, modern surveys operate on an entirely different scale. The forthcoming Vera C. Rubin Observatory, slated for full operation in the near future, will image the entire visible sky every few nights using an 8.4-meter telescope equipped with a camera boasting 3.2 billion pixels. Each night it is expected to generate approximately 20 terabytes of raw data, detecting roughly 10 million transient or moving objects. This is not an exaggeration. 10 million alerts per night, each potentially signifying something of interest. An asteroid, a supernova, a variable star, a cosmic ray impact, or an instrumental artifact. No human team can possibly review 10 million alerts nightly and make informed decisions about which warrant follow-up. Automation is essential. Machine learning algorithms trained to recognize patterns, classify objects, and flag anomalies are indispensable. This is the domain of artificial intelligence, and it is revolutionizing astronomical practices. The fundamental methodology employs supervised learning. A neural network is trained using labeled examples. This is an asteroid, this is a distant galaxy, this is a cosmic ray, this is instrumental noise. The network then learns to identify features within images and spectra that differentiate these categories. Once trained, it can process new observations automatically, assigning classifications and confidence levels. For routine objects, this process is remarkably effective. AI classifiers can identify asteroids, ascertain their approximate orbits, and flag those that may be near-Earth objects requiring immediate tracking. They can detect supernovae in distant galaxies, classify variable stars, and identify gravitational lensing events, all automatically and at scale with accuracy comparable to or exceeding that of human experts. However, a fascinating tension exists here. Artificial intelligence excels at identifying what it has been trained to recognize, but can be profoundly inept at identifying novel phenomena that fall outside its training parameters. If a network is trained exclusively on images of typical solar system asteroids and comets, it will learn to recognize what constitutes typicality. When an interstellar object like Oumuamua appears, behaving unlike either category, the AI might misclassify it, assign it a low priority, or flag it as a probable false detection. The very efficiency that enables AI to process millions of observations can also render it oblivious to genuine novelty. This is why anomaly detection represents a distinct and critical approach. Rather than asking into which category an object belongs, anomaly detection investigates how significantly it deviates from all previously observed phenomena. This involves unsupervised learning. The algorithm is not provided with labeled categories. Instead, it learns the inherent distribution of properties within the data and flags outliers. An object exhibiting unusual motion, peculiar coloration, anomalous brightness variations, or any other properties situated far from the norm would be automatically flagged. Oumuamua was initially detected by the ATLAS survey, which employs automated detection but relies on classical algorithms rather than deep learning. The object was flagged due to its trajectory. It was not moving like a solar system body, suggesting its origin in interstellar space. However, one must ponder whether this object, had it arrived a few years hence when AI classifiers are managing the majority of survey operations, would have been promptly flagged, or might it have been initially misclassified, potentially delaying follow-up while more routine objects received telescope time? These are not purely hypothetical scenarios. Research groups are actively developing AI systems for the era of the Naves Observatory. One approach involves training networks on simulated interstellar objects, teaching the AI to recognize distinguishing features. Another utilizes anomaly detection to automatically flag anything unusual, irrespective of whether it fits predefined categories. A third approach combines classification and anomaly detection in a hybrid system, classifying routine objects efficiently while maintaining a separate anomaly stream for objects that do not align well with any established category. The implications extend beyond the mere identification of interstellar visitors. Artificial intelligence is currently undergoing training to identify sudden releases of material from comets, pinpoint active asteroids, detect unusual light spectrums, and correlate observations across various wavelengths. Theoretically, an AI system could have flagged 3IATLAS, not merely for its peculiar movement, but for the discrepancy between its measured acceleration and its visual presentation. A neural network could be developed to recognize the indicators of gas release, the formation of a coma, the development of a tail, and characteristic fluctuations in brightness. It could then flag objects exhibiting acceleration without these accompanying signs as anomalous. This type of comprehensive anomaly detection has the potential to reveal subtle oddities that human observers might overlook. Nevertheless, challenges persist. AI systems can be fragile, failing unpredictably when confronted with rare or extreme circumstances. They can also inadvertently absorb biases present in the data used for their training. For instance, if an AI is primarily trained on bright celestial bodies due to their extensive study, it might perform poorly when examining dimmer objects. Furthermore, these systems can generate false alarms, inundating astronomers with erroneous alerts. Often they function as black boxes, making decisions based on learned patterns that are not easily decipherable. When an AI designates an object as anomalous, understanding the rationale behind that determination can be exceedingly difficult. There's also the significant question of whether AI might entirely miss truly groundbreaking objects, simply because they deviate too drastically from established norms. Imagine an artificial probe designed by an intelligence employing engineering principles entirely alien to human conception, traversing our solar system. Such an object might present observational signatures unlike any natural celestial body. An AI trained exclusively on natural phenomena might not even recognize it as noteworthy, potentially classifying it as mere noise, an instrumental error, or something too bizarre to fit any existing model, and therefore likely a false reading. This represents the less desirable aspect of automation, achieving efficiency at the expense of unexpected discoveries and prioritizing classification over genuine exploration. Human intuition and expert judgment remain indispensable. The optimal system would integrate the efficiency of AI with vigilant human oversight. Algorithms should manage the vast majority of routine celestial objects while surfacing genuinely peculiar ones for expert human evaluation. This necessitates the development of tools that facilitate astronomers' review of AI decisions, enabling them to investigate flagged anomalies and override classifications when expert knowledge indicates otherwise. It also calls for fostering a culture of inquisitiveness, where unusual objects are not hastily dismissed as errors, but are thoroughly investigated to glean what insights they might offer. Looking ahead, the role of AI in astronomy is poised for continued expansion. The sheer volume of astronomical data is escalating at a pace far exceeding the growth of the human workforce. This presents both opportunities and responsibilities. The opportunity lies in discovering rare objects, identifying subtle patterns, and processing information with an efficiency unattainable by humans alone. The responsibility entails ensuring that we do not systematically overlook critical phenomena, preserving the human elements of curiosity and intuition, and maintaining humility regarding the limitations of our current models and classifications. The object known as 3IATLAS serves as a crucial test case for our capacity to navigate this transition. We have detected it, we are actively studying it, yet we are also grappling with its fundamental nature. The AI tools we develop in the coming years will dictate whether future interstellar visitors receive the attention they warrant or pass through our observation systems unnoticed. Part 13. The tempest that should have reshaped everything. Envision this scenario. It is early November in the year 2025. The sun, exhibiting one of its most ferocious outbursts in recent memory, unleashes powerful jets of plasma traveling at 1,000,000 miles per hour. Magnetic fields twist, rupture, and then realign. Solar storms of such intensity paint auroras across latitudes that seldom witness such phenomena. And precisely amidst this cosmic turmoil, 3IATLAS, having recently completed its closest pass by our star, navigates its course. Any typical comet would have reacted with extreme vehemence. Here's what you must grasp regarding solar storms and their interactions with smaller celestial bodies. The sun is not merely a passive radiator of light and heat. It possesses a dynamic, pulsatile nature. During periods of heightened activity, it expels immense clouds of charged particles into space known as coronal mass ejections, which carry their own complex magnetic field configurations. When these solar storms collide with a comet, a cascade of events unfolds. The charged particles engage with any surrounding gas emanating from the comet's nucleus, ionizing it and causing it to emit light. The magnetic fields can entwine with the comet's own induced magnetosphere, generating electrical currents that heat its surface. Perhaps most strikingly, the increased influx of high-energy particles can literally ablate material from the comet's surface, atom by atom, akin to molecular-level sandblasting. A scientific paper published in March of 2025 by researchers at the Southwest Research Institute meticulously examined precisely this phenomenon. Their study investigated the impact of solar storms on the volatile activity of small celestial bodies during their closest approach to the sun. Their modeling was both sophisticated and exhaustive. When a standard comet is exposed to a potent solar storm environment, one would anticipate observing intensified gas release, surges in dust ejection, and even sudden outbursts where subterranean pockets of ice vaporize. The storm doesn't just passively warm the surface. It actively erodes material through a process termed ion sputtering, where energetic particles physically dislodge molecules from the comet's surface. The research incorporated historical data from comets that passed near the sun during periods of high solar activity. The correlation was irrefutable. Intense solar activity led to increased cometary activity. An elevated particle flux directly correlated with enhanced gas release. This fundamental physics has been confirmed across numerous objects and over several decades of observation. 3IATLAS encountered these very conditions in late October and early November of 2025. The sun was in an active phase and solar storms were propagating outward. Some of these storms would have intersected the object's trajectory within days of its perihelion, a time when its surface was already intensely heated, and any volatile ices should have been sublimating rapidly. The outcome? Nothing. No tail, no coma, no observable outburst. This is where the anomaly transitions into profound strangeness. We are not discussing a minor deviation. We're referring to an object that has defied one of the most robust predictions within the field of cometary science. Solar storms are expected to trigger activity. They consistently have. Every comet studied during active solar periods has exhibited some form of response: increased brightness, expanded tails, spikes in dust production. The underlying physics is too fundamental to disregard, unless, of course, the object simply lacks the necessary material to react. Consider the implications of this. Either 3IATLAS possesses a surface composition so unconventional that solar storms merely deflect off it, or it is entirely devoid of volatiles. Both possibilities are highly unusual and fundamentally challenge our existing assumptions. Some researchers are now positing the existence of surface states previously unobserved. What if, during its interstellar journey, the object developed a metallic outer layer? The persistent bombardment of cosmic rays over millions of years could have altered its chemistry, forming a hardened crust resistant to both thermal and particle-induced erosion. Alternatively, perhaps it's not merely a crust, but the inherent composition. It might be a mass of metal-rich material, potentially originating from a shattered planetary core in another star system, encased in a thin layer of carbonaceous compounds. Either of these scenarios would effectively explain its resistance to solar storm effects. Metals do not sublimate at such temperatures, and carbon compounds can exhibit remarkable stability. If the surface is predominantly composed of these materials rather than water, ice, or other volatiles, then solar storms become largely irrelevant. The forces would be attempting to erode something that is inherently resistant to such conditions. The ramifications of this discovery extend broadly. Our understanding of near-small body physics, which we believe to be well established, might be far more dependent on surface composition than we previously recognized. We formulated our models based on observable objects, icy comets, rocky asteroids, and their combinations. But what about objects that remain undiscovered? What about compositional categories we have yet to encounter? 3IATLAS might be revealing a significant blind spot in our scientific comprehension. We operated under the assumption that all comets respond to solar heating and storms in predictable ways because every comet we had studied adhered to this pattern. However, this is a clear case of selection bias. We were studying only those objects that persisted long enough to become observable, those that outgassed sufficiently to develop tails, those that fit our preconceived notions. What we believe to be true about cometary interactions with the sun is being fundamentally questioned by this single object. It is a solitary data point, certainly, but one that stubbornly refuses to conform. And in the realm of science, outliers are frequently the most illuminating. They are the anomalies that compel us to broaden our theories, to scrutinize our assumptions, and to approach established problems with fresh perspectives. However, another potential explanation exists, one that sounds like science fiction but has garnered considerable scientific attention in recent years. What if we're not dealing with a naturally occurring object at all? Part 14. When scientific inquiry intersects with speculation. Allow me to transport you back to October of 2017, the epoch of Oumuamua's discovery, the first confirmed interstellar object to traverse our solar system. Within weeks, the scientific community was abuzz with discussions. Within months, serious researchers at reputable institutions began posing a question that would have seemed utterly absurd just a few years prior. Could it be artificial? The notion, while startling, was not entirely unfounded. Oumuamua presented peculiarities: an exceptionally elongated shape, a high degree of reflectivity, and an acceleration pattern that didn't quite align with conventional outgassing models. Harvard astronomer Avi Loeb proposed the intriguing possibility that it might be a light sail, a manufactured artifact utilizing solar radiation pressure for propulsion. While the broader scientific community largely dismissed this hypothesis, the seed of doubt had been sown. We had entered an era where interstellar visitors demanded scrutiny not just for their inherent natural characteristics, but also for any potential indicators of artificial origin. Fast forward to the year 2025, and this rigorous examination has become systematic. Several research collectives, including teams affiliated with the SETI Institute, have developed specific protocols for monitoring interstellar objects. Upon the identification of 3IATLAS as a potentially interstellar visitor, these protocols were immediately activated. Telescope observation time was allocated, radio telescopes were directed toward the object's trajectory, and optical and infrared instruments were focused on its position, all in search of any evidence suggesting non-natural origins. The fundamental question is not whether we should investigate, but rather how we should approach this investigation and precisely what signatures we should be seeking. Differentiating between natural and artificial objects in space is considerably more challenging than one might initially assume. Nature is capable of producing remarkably ordered patterns, crystalline structures, orbital resonances, and even the hexagonal storm systems observed on Saturn all appear deliberately engineered, yet they emerge from fundamental physical laws. Conversely, not every artificial object presents as obviously manufactured. A derelict probe drifting through space for eons might become pitted, darkened, and eroded to the point where it closely resembles a natural rock. So, what specific signatures do we actively search for? Several categories emerge as crucial. Firstly, anomalous motion. If an object exhibits tumbling patterns indicative of attitude control, or if its acceleration profile suggests propulsion rather than gas release, these are significant indicators. Secondly, electromagnetic emissions. This includes narrow-band radio signals, laser pulses, or any form of transmission that deviates from natural phenomena. Thirdly, material properties. Objects with highly reflective surfaces or unusual spectral signatures might suggest the presence of engineered alloys or composite materials. Fourthly, geometry. Significantly large area-to-mass ratios that exceed natural formations or shapes that imply functional design rather than random accretion are of interest. 3IATLAS exhibits characteristics that align with some of these criteria. Its observed acceleration, despite a conspicuous lack of outgassing, is unusual. Its potential metallic and carbon-rich composition is atypical for a comet. The compact star-like appearance devoid of any diffuse envelope is also noteworthy. Individually, none of these observations conclusively prove artificiality, but collectively they form a profile that warrants considerable attention. The Breakthrough Listen initiative, which employs radio telescopes to detect signs of extraterrestrial intelligence, added 3IATLAS to its target list in late October of 2025. They are meticulously scanning the object across multiple frequency bands, searching for any signal that might suggest technological origins. Thus far, the results have been negative. No narrow band emissions, no readily apparent transmissions. However, the absence of evidence is not definitive evidence of absence. A derelict probe, for instance, might not necessarily be transmitting, and a fragment of manufactured material would not be expected to emit any signals at all. This is precisely where scientific caution becomes paramount. We cannot precipitously leap from this object is unusual to this object is artificial without an overwhelming amount of evidence. The burden of proof is immense, and rightly so. Extraordinary claims necessitate extraordinary verification. Every plausible natural explanation must be thoroughly exhausted before we seriously entertain an artificial hypothesis. Nevertheless, let us entertain it for a moment, clearly demarcating this as speculation, as this is where the narrative becomes genuinely intriguing. If 3IATLAS were indeed artificial, what might its nature be? Option 1, a derelict probe. Imagine it as a celestial equivalent of our Voyager spacecraft, launched eons ago by some advanced civilization now drifting aimlessly through the galaxy. Its systems would long have failed, its original purpose possibly forgotten even by its creators. It would simply be an artifact of ancient technology, a cosmic fossil. Option 2, a manufactured fragment. It might not be an intact probe, but a component of something far grander. Perhaps a piece of large-scale planetary engineering, a fragment originating from a Dyson swarm, or even debris from an industrial accident, on a scale that defies our current comprehension. It would be artificial, certainly, but not necessarily dispatched with a specific destination in mind, simply drifting detritus. Option 3, and this is where the concept becomes truly peculiar, an interstellar marker, or buoy. It could be a deliberately placed marker or a relay station, perhaps part of an unseen network. It might not be transmitting because we are not tuned to the correct frequency, or because it operates only under specific conditions, or perhaps it is simply awaiting an action on our part that is yet to occur. All of these possibilities sound like pure science fiction. All of them are statistically improbable. However, the universe is vast and ancient. If technologically advanced civilizations exist elsewhere, and if even a minuscule fraction of them engage in interstellar endeavors, then the discovery of their artifacts is not an impossibility, merely an improbability. Here lies the exciting aspect. We are no longer solely astronomers. We have become cosmic detectives. We are meticulously gathering evidence, systematically eliminating possibilities, and posing questions that blur the lines between astrophysics and entirely different domains of inquiry. Regardless of whether 3IATLAS proves to be natural or artificial, the very fact that we are seriously contemplating such a question signifies a fundamental shift in our approach to interstellar objects, and the investigation continues. New data streams in on a weekly basis. Observatories across the globe and in orbit are diligently tracking this object, meticulously measuring every conceivable parameter. What we discover may not only rewrite our understanding of small celestial body composition, but could potentially redefine something far more profound. In either case, the coming months will be critical, as 3IATLAS will not remain within our observational range indefinitely. Part 15, the closing window. Time is our most significant adversary in this endeavor. 3IATLAS achieved its closest proximity to the Sun in late October of 2025. Since then, it has been accelerating outward, moving progressively farther from both the Sun and Earth, diminishing in brightness with each passing day. Within a few months, it will become inaccessible to most ground-based telescopes. Within 1 to 2 years, only the most powerful instruments will retain the capacity to detect it. Eventually, it will fade into the profound darkness between the stars, becoming another enigma that briefly visited, leaving us with more questions than answers, unless we act with urgency. The James Webb Space Telescope is scheduled to observe the object in December of 2025 and January of 2026. These observations will involve deep imaging and spectroscopy, utilizing instruments sensitive enough to detect trace elements and organic molecules if they are present. This data could be pivotal in resolving the question of its composition. Will it reveal metallic and carbon elements, or have our interpretations of the limited spectral data gathered thus far been mistaken? The Webb telescope is expected to provide definitive answers. Ground-based observatories are also mobilizing for follow-up observations. The extremely large telescope in Chile and the giant Magellan telescope, both of which commenced operations in the early 2020s, are planning crucial follow-up studies. Their colossal mirrors possess the capability to collect sufficient light to study 3IATLAS, even as its brightness wanes. These observations will focus on its rotation rate, any discernible surface features, and continued monitoring for any indications of gas release or activity. Preliminary discussions have even emerged regarding the deployment of small satellite missions, such as CubeSats or similar platforms equipped with cameras and spectrometers, launched on trajectories that could intercept or at least observe 3IATLAS from a closer vantage point. While these missions present significant technical and financial challenges, the potential scientific return would be immeasurable. Direct in situ observation remains the gold standard, and nothing answers questions as definitively as being physically present. Furthermore, the ultimate aspiration involves either sample return or rendezvous mission. Imagine a spacecraft successfully intercepting 3IATLAS, matching its velocity, and conducting detailed observations for an extended period, potentially months or even years. Envision that spacecraft collecting physical samples, fragments of an interstellar traveler, and transporting them back to Earth for rigorous laboratory analysis. We would glean more from a single gram of 3IATLAS than from thousands of hours of telescope observation. While not currently funded or definitively planned, this ambitious concept is actively being discussed. Space agencies are paying close attention, as are private enterprises. The appetite for missions targeting interstellar objects is steadily growing, and 3IATLAS represents precisely the kind of target that could justify such a substantial investment. What might we learn if the object is indeed metal-rich, containing iron, nickel, and carbon in unusual configurations? We would be compelled to establish a new category within our existing taxonomy of small celestial bodies. Currently, we classify objects as comets, asteroids, Kuiper Belt objects, and interplanetary dust. Where then would a metal and carbon-rich interstellar visitor fit? How do such objects originate? Are they fragments from planetary collisions in distant star systems, or do they represent something entirely novel that has not been observed in our own solar system? The implications for planetary formation models would be profound. If other star systems routinely produce metal-rich ejecta that escapes into interstellar space, then the compositional diversity of planetary systems across the galaxy might be far greater than we currently envision. Conversely, our own solar system could be an outlier, unusually depleted in certain elements, with 3IATLAS offering a glimpse into the typical composition of planetary systems elsewhere. Even if 3IATLAS ultimately proves to be entirely natural and fully explainable, its demonstrably different behavior compared to every comet we have previously studied necessitates an expansion of our expectations. We must prepare ourselves for unforeseen surprises and accept that the universe may be more varied, more perplexing, and wonderfully more intricate than our current theoretical frameworks allow. And more surprises are indeed on the horizon. The Naves Observatory in Chile, equipped with its powerful legacy survey of space and time telescope, commenced full operations in 2023. It systematically scans the entire visible sky every few nights, cataloging every object that exhibits movement or change. While its primary mission focuses on the study of dark energy and dark matter, a significant incidental benefit is its capacity to detect interstellar objects, and in substantial numbers. Projections indicate that the Naves Observatory will detect one interstellar visitor annually, and potentially more. We're entering an era defined by the statistical analysis of interstellar objects. Instead of studying Oumuamua, Borisov, and 3IATLAS as isolated curiosities, we will possess sufficient sample sizes to draw meaningful conclusions. What constitutes typical behavior? What is rare? What range of compositions and behaviors exist out there in the vastness of the galaxy? This marks the advent of interstellar object population 2.0, the era when we transition from being surprised by each new visitor to developing a comprehensive understanding of what travels between the stars. However, it is imperative not to overlook the human dimension inherent in this remarkable narrative. Presently, in November of the year 2025, our attention is fixed upon a celestial body originating from beyond our stellar neighborhood. This entity, conceived around a sun distinct from our own, has journeyed for untold ages through the cosmic expanse. It carries within its very composition the chemical essence of worlds unknown to us. We are currently engaged in its real-time examination. New data is disseminated on a weekly basis. Observational efforts are meticulously coordinated across multiple continents. Scientists are actively engaged in interpreting the findings, refining their theoretical frameworks, and suggesting further avenues of investigation. This is the very essence of scientific discovery in motion, a process marked by its inherent complexity, its thrilling revelations, and its undeniable uncertainties. No existing scientific text holds the definitive answers, for such answers have yet to be formulated. We are collectively authoring this knowledge piece by piece through each observation, each published paper, and each night dedicated to telescopic study. Whether Oumuamua proves to be a metal-rich fragment of a long-shattered exoplanet, a carbonaceous remnant of interstellar chemical processes, or indeed something far more extraordinary, it has bestowed upon us an invaluable gift. This brief visitation offers a glimpse into the vastness of the galaxy, a profound reminder that our solar system is not an isolated entity. It underscores our existence within a grand cosmos where celestial objects traverse the interstellar void, arriving bearing tidings from afar. We must embrace this momentous opportunity with urgency. The fleeting window of observation is rapidly diminishing. Oumuamua is steadily fading from our view, yet the profound questions it ignites will undoubtedly endure long after its departure into the darkness. So what do you surmise it truly is? A comet unlike any previously encountered? A fragment from the core of an alien planet? A natural marvel that defies our current classifications? And what new insights await us when the data from the James Webb Space Telescope becomes available? When the subsequent phase of observations is completed, and when another interstellar visitor graces our telescopes, the universe is dispatching emissaries to us. These are peculiar travelers from the immense void between star systems. The critical question is whether we are adequately prepared to comprehend their messages, whether we possess the courage to transcend the familiar and welcome the extraordinary. Stay engaged. Monitor the ongoing data releases. Devote attention to the burgeoning scientific publications, for this narrative is actively unfolding before us, and you are a witness to its unfolding. Oumuamua continues its outward trajectory, accelerating away from us, returning its mysteries to the cosmic abyss. But before its final departure, before its light completely recedes, we have a singular opportunity to grasp the significance of what we are observing. A final chance to unravel this enigma. One last opportunity to comprehend the nature of that which traverses the darkness between the stars.